Hello everybody, I hope you're enjoying your snow day in Las Vegas. So what I want to do today here is go ahead and talk through the remainder of the lecture for aromatic compounds that we were supposed to go through today. So just a recap of last time. So last time we went over all the different aromatic reactions, these 5 main ones. We call these electrophilic aromatic substitution reactions. These are the 5 main reactions that I want you guys to know about. So first we have the halogenation reaction, where we add a chlorine or a bromine. Next we have nitration, where we add a nitro group. The sulfonation reaction, which we'll talk about later, but we typically use it as a protecting group. And then we also have the set of Friedel-Crafts reactions, where we can add alkyl groups or acyl groups to these compounds. Also, as a reminder, we cannot do addition reactions with benzene compounds very easily because of the fact that they lose their aromaticity and it's very high delta G of activation. Interestingly, it turns out that all 5 of these reaction mechanisms happen pretty much in the exact same way. The main notable difference is the way that we form the electrophile. So here, last time we went over the fact that you do need a strong electrophile for this reaction to work, and or you need your benzene to be activated with the donating group. After the electrophile gets attacked by the nucleophile from the benzene, we do get the formation of this rhenium ion that is resonance stabilized. And here we see that plus charge get pushed around the ring, all the way to the end where we get the E1-like elimination. I do want to note here that if I do ask you guys for a mechanism, I am expecting to see the resonance of the rhenium structure, the rhenium ion. Here we did talk about the energy of activation of this reaction. Once again, note that the first step here has a very large energy of activation, and this has to do with the formation of the carbocation because we're technically losing aromaticity with the formation of the carbocation. However, the elimination step, the very last step, is very quick and low energy of activation because we are restoring the aromaticity. All right, so all we have to do really is take a look at how we form all the different electrophiles in these reactions and then look at the little details in their mechanism. They're all pretty much the same for the most part. All right, so here first I have the mechanism for the halogenation. So in the first step of the reaction, we're going to see that the reagents are going to react with each other. So here I have Br2 reacting with iron 3 bromide, which is actually a pretty strong electrophile. And then we get this strange electrophile intermediate. When you see this type of reagent, you basically want to think of it as a Br plus ion. Note that these technically do not exist, but we think of it that way in the reaction mechanism. All right, so here we see the benzene attacking the bromine, and it's going to generate FeBr4, which will then act as the base later in our reaction. So then we have the rhenium ion, which can then undergo resonance. Remember, when practicing these resonance structures, you want to chase the positive, essentially, and that will push the plus charge around the ring until you get to the point where it's right next to the carbon that has the new group. And then in this step here, we show a bromide ion acting as a base in an E1-like elimination, going back to the alkyl bromide. And that's pretty much it. So just like the generic reaction for this part, the only thing different are the actual specific details of the actual reagents that we're working with. And the main thing that's different is the first part here. The next reaction I have to look at is a little bit more complicated, but it's just like this other one, it's pretty much the same. So here we have the mechanism for the nitration reaction. In this reaction, we first see that the concentrate of sulfuric acid and nitric acid can react with each other. Typically, you think of both of them as a pretty strong acid, and they typically don't do reactions like this. However, I did write the pKa's for both sulfuric acid and nitric acid. And you may notice here that this reaction can occur due to the difference in the pKa's. And then we do get a very high energy intermediate. Notice in this particular compound, we have adjacent-like charges, which will then rapidly eliminate the water group to give us the so-called nitronium ion NO2+, which we use as our electrophile, which, this is pretty high energy. It doesn't want to be this way. It's definitely going to react with a nucleophile. And we see that with benzene. So benzene will act as a nucleophile, attacking the nitrogen in the nitronium ion. And then we get our standard resonance structures for the rhenium ion intermediate. Once again, we want to chase the positives, pushing that plus around the ring. And then we get the final elimination step. I do want to point out that as a good way to study this is to remember the positions of the plus charges. And relative to the new group coming in, the plus charges always end up being ortho, para, ortho. So you can use that as a way to remember this. So the plus charge in all these mechanisms never end up on the metacarbon. It's always on ortho, para, ortho. All right. I'd ask any questions, but you guys aren't here, right? Next reaction here is the sulfonation. This one is probably the most straightforward out of all the different ones that we go over. So in this particular reaction, we're using fuming sulfuric acid, which, if you recall from last time, fuming sulfuric acid is very concentrated, so much so that it has a SO3 gas floating on top of the solution. So the SO3 is actually our electrophile already made for us in the reaction. So here we see that benzene can act as a nucleophile, attacking the sulfur atom. I did want to point out that all these oxygen groups make that sulfur very delta positive, meaning it's electrophilic. And then, just like before, we go ahead and see the rhenium ion resonance stabilized, ortho, para, ortho, and then we get the elimination step. Don't forget that at this point you are technically not done with the reaction. We are in an acid solution, and you should go ahead and protonate the OH group here to get the final sulfonic acid product. All right, the last set of reactions here are very useful. These are the Friedel-Crafts alkylations. I say they're useful because they're great ways to extend carbon chains onto benzene rings. Extremely useful. In this case, the C+ is our electrophile. So what happens here is we have aluminum trichloride, and I have here an alkyl halide. Typically, it's done with chlorides, but it can be done with bromides as well. So first things first, we have to show the formation of the electrophile. So here we see the lone pair on the halogen can attack the electrophilic aluminum atom. And then at this point, we have this particular intermediate. And it turns out that this particular group can act as a great leaving group, giving us a carbocation. So I do want to point out that I'm showing this like an SN1, but if this is a primary halide, it works just the same. And we go ahead and get an SN2. But we'll see, but it ended up working out, that it's mostly SN1 route for this particular carbocation. So here I'm showing the plus charge being attacked by the nucleophilic benzene. You go ahead and get the rhenium ion, just like the other ones, ortho, para, ortho. And then lastly, we show the reformation of the catalyst by showing the AlCl4- acting as a base in the E1 elimination step, generating our benzene back and HCl side product. I do want to mention in all these reactions, if we're using a catalyst, we should show them being reformed in their reaction mechanism. Because the electrophile in this particular reaction is a carbocation, we do have some alternative approaches we can use for this, and we also have some pretty significant limitations with this reaction because of the fact we have a carbocation. And remember, carbocations can rearrange, so we don't always get the products that we want. So first application I want to show you guys, an alternative application, is here. So it turns out that we can actually use an alkene as our electrophile here, as long as it is in acidic conditions. So in this particular example, I'm showing this one propene with hydrofluoric acid. The way this one would work is you would get addition of H to this carbon here, and then you would generate a carbocation with a plus charge here, Just like we saw during the addition reactions to alkenes, the main difference here now is that instead of the fluorine coming in and attacking, the benzene is going to come in and attack as a nucleophile. And we end up getting a net addition to the alkene. And so instead of the F here, we now have this whole benzene group here. So just as I mentioned just a second ago, we do have carbocations, so we do have a problem here when we're trying to work with certain types of substrates that can rearrange. So here I'm showing that if we have a primary halide, we do not get the primary alkyl chain on here, and the reason why is because if we backpedal a little bit, this particular carbocation will form this carbocation via rearrangements. So then what happens here, if you're trying to work with a primary carbocation intermediate here, what ends up happening, you get the secondary one instead. And then here down below, I'm showing that if we have this type of alkyl halide, this can rearrange as well, giving us a tertiary carbocation, which we also once again get a rearranged product. So in this case here, we're seeing a secondary carbocation rearranging to a tertiary carbocation. I recommend that you practice these mechanisms. The only difference is that when you're at, say, this step here, you can have a rearrangement. So what I would do is, if these are primary, just go ahead and show the formation of a primary carbocation. You know, I don't like showing that kind of stuff, but then you just show it rearranged as secondary. We do have an alternative that we can use instead. If you want to make sure that you're getting a primary alkyl chain on there, the better approach is the acylation reaction followed by a reduction. So here, remember that the conditions are very similar. So instead of using an alkyl halide, we'll use an acid halide instead. And here I'm showing use of an acid chloride. Recall that the way that we make these is that you take the corresponding carboxylic acid, and then you treat it with SOCl2 or PCl5, and I believe PBr3 would work here as well. This reaction also works with anhydrides. So essentially what we have here is we have a carbonyl carbon with a really good leaving group, and that's the general case for working with anhydrides or even the acid halides. All right, and then we go ahead and have the mechanism. It's similar to what we saw with the alkylation reaction. So instead what happens here is the chlorine lone pair attacks the electrophilic aluminum, and then we get a leaving group here, and we get a really strange intermediate called the acylium ion, like so. And I do want to point out that this is high energy, but it's resonance stabilized, so we can show its formation. So here we can show resonance for it. I do want to point out that if you're proceeding to the next step, you can use either one of these. And the only difference is that if you look at mine down here, I start with this one, and I have to get this extra arrow push, which basically pushes it to look like that one. So if you start with this one here, you don't need the second arrow push right here. It just attacks directly. And then carbon have the full octet. All right, so after you have the nucleophilic attack, you go ahead and show the standard, resonance of the rhenium ion. Just like the previous ones, the plus charge goes ortho, para, ortho. And then the very last step, you want to go ahead and show the base coming in, giving you your E1 elimination, leading to the final product. All right, so what we can do here, once again, just to summarize, we do have some limitations. It works out where we do have carbocation rearrangements. The other limitation here that's pretty significant in my opinion is that we can't use phenyl or vinyl halides. Remember, these are the kind of halides that have the chlorine directly on a double bond. And it works out that we can't do these kind of reactions because you don't want to show the formation of a carbocation directly on a double bond. They are very high energy. So what ends up happening is no reaction. We do have other ways to achieve these reactions. Additionally, I did mention earlier that we do have alternative ways to achieve this. Substitution of a primary alkyl group, and I'm showing that here. It's the so-called Clemmensen reduction. So essentially what you do, starting with benzene, if you want to get the primary alkyl group on there, what you do is you do the acylation, not the alkylation. And then following the acylation, you then want to go ahead and do the Clemmensen reduction, which requires the use of a zinc-mercury amalgam, HCl, and heat. And I do want to point out this is the net reduction step. It's a little bit different than the reduction we've seen before in that we actually fully lose the carbonyl carbon. It does not become an OH, it becomes just the two H's. From my understanding, this reaction pretty much works best if you have the carbonyl carbon in the benzylic carbon. I don't really see this used all that much when we're reacting with ketones that are in a straight chain. We have other ways to do this. So what I want to go ahead and do here is provide an example on how we do this. So here I have an example where I want to go ahead and try to make this particular compound. Notice here it is a primary halide. So if I try the approach where, starting with benzene, like, oh, I can just go ahead and choose propyl chloride, AlCl3, and as we saw in the notes earlier, what ends up happening is that we get the rearranged product here. So we get the isopropyl group instead. So once again, you want to think about, just like we saw with SN1s, that if we have a primary carbocation, they're going to rearrange. All right, so the alternative approach is to start with benzene again. And I want to use the corresponding acid halide now here. So essentially what's going to happen is the benzene is going to attach where the chlorine's at. I often like to show the formation of these acid chlorides because they typically are not purchased directly because they're so reactive. They're oftentimes made fresh if we're going to work with them. So here I have the corresponding, carboxylic acid. And you guys would know how to make this from an alcohol if that was a different starting point. But all you do here is just say SOCl2, boom, we got our acid chloride that we can then use in our Friedel-Crafts acylation. Don't forget here that we do need an AlCl3, like so. And we go ahead and put this group on here. I also do want to point out that we do have a limitation, another limitation with these kind of compounds, is that going back to this one here, notice how on this particular compound we are adding a alkyl group, which if you recall your groups, that is the donating group. And what that means is that this compound is actually more reactive than the one that we started with. So what ends up happening a lot of the times with these alkylation reactions is we could potentially get multiple alkylations. And it's difficult to control that. So that's one limitation here. Where with the acylation, you're more likely to get a single substitution because of the fact that we're adding a withdrawing group on there. And it works out where this compound is less reactive than the one that we're starting with. So it is less likely to do a second acylation here. All right, the next thing I want to go over is so what happens if you already have a particular group on there, and if you're trying to do a second substitution or a third substitution, what happens? So here, we're going to say we have some generic group Y, and there's different things that happens if Y is a donating group or a withdrawing group. So if we have an EDG, electron donating group, recall those groups were things like your alkyl groups, so CR3, and then we have our amines, NR2, and then we have our alcohols and ethers, so NOR lone pair. So I just want to point out this can be an OH or an O carbon. It doesn't really matter. What ends up happening is that if you add a group on here, after you already have one on there, this group will dictate where the next group goes. So what ends up happening is that if you have one of these groups on there, they direct ortho and para. So they direct ortho, comma, para. So if I were to go ahead and do another EAS reaction, the group would probably have a preference to go to the para position. And the reason why we do get some of the ortho product, but usually ends up working out where para is major, and that's just due to steric hindrance. Oftentimes, why the bulky group, which kind of blocks the ortho position for a new incoming group. So we typically get the para product from this instead. I am going to go over the mechanism on why this works this way. I just want to give you the general overview right now. All right, and then in the reverse case, we have an EWG. It works out where EWGs, such as if we have a alkyl group with a bunch of halogens on it, that's a withdrawing group. And then we have the strongest one of the bunch, the NO2 group, is withdrawing. And then we can have a protonated amine. So I'm going to put this as NHR2+. Notice the difference here. This is protonated. This is deprotonated. That is going to come into play in a few of the reactions here. And then if you have a carbonyl carbon, that's a withdrawing group. And then the other one I want to mention here is the cyano group. Okay. These particular groups, they direct meta. So if I were to add a group on there, if Y with the withdrawing group, it's going to have a preference to put the second group in the meta position. Does not matter what you're actually putting on there, it's what's already there that makes the difference here. It directs meta. We do have an oddball in the withdrawing category, and this is the halogens. It turns out that while they are withdrawing groups, these ones actually direct orthopara. So these direct orthopara, but they're in the category of withdrawing groups. Okay, so if you recall from the mechanisms here, we are always showing benzene acting as a nucleophile, meaning that if you have donating groups on there, you are making this benzene ring more electron rich, which makes it a better electrophile. It makes these ones more reactive. So these are more reactive with donating groups because benzene is a better nucleophile now. And then for the withdrawing groups, these are less reactive. And that's because you're pulling electron density away from benzene, making it a worse nucleophile, so the reactions do not work as well. All right, so there are a couple ways that we can explain the reactivity as well as the directing power by looking at two different things. One of them is the mechanism of the actual substitution, and we're going to see there's differences in these patterns here depending on where we put the group at. The additional thing you can do is you can also draw resonance structures of the compound before it reacts, and we can see that they're going to have a tendency to direct orthopara for the donating groups. So let's go ahead and take a look at the donating groups, and I want to take a look at some resonance first, and then we'll look at a reaction, and then we'll do the same thing with the withdrawing groups. All right, so here I'm going to go ahead and say that we have benzene, and let's go ahead and just make it a phenol OH group. So this is the donating group. And I want to go ahead and show the resonance here, and we're going to see in the resonance here why we call them donating groups. So this lone pair, so in all the donating groups, we have lone pairs on the atom directly attached. So you go ahead and show this push towards the ring, and then this has to jump up over there to make it not violate the octet rule. So we go ahead and draw the result. So benzene ring, we have a lone pair here now, negative, double bond to oxygen, H, and then that still has a lone pair on there and a plus charge. All right, so we get that resonance structure. On these resonance structures, we're going to push negatives around the ring now. And I want you to take note on the positions that they're going to. So here we show the next resonance structure. Notice how the way I push the arrows here, the lone pair started at ortho, and then it ended up going to para. So let's go ahead and draw that. So that double bonds there, negative on the bottom here, and then we have this. Just a little side note about resonance. Remember, you're doing resonance structures correctly if the sum of the formal charges is the same from one structure to the next. So I started out neutral. It needs to be overall neutral from every single structure here on out. And it's going to work out where we have a plus minus on all these, making it effectively 0. All right, next resonance structure, we're going to go ahead and push this lone pair to the ortho position on the other side now. So that. So we go ahead and draw out this resonance structure. We get a lone pair over here. new double bond. This one didn't move yet, or moved earlier. And then here we have this intermediate. All right, and then we can do one more resonance structure, giving us our benzene back, like so. And we get our benzene compound back, like this. All right, so what we're showing in all these resonance structures here is that benzene is more electron rich now than it would have been normally. So we say this is activated because these benzenes are electron rich. If you take a look at the overall resonance hybrid, we can use this to explain why this is an orthopara director. So drawing the resonance hybrid, we only show we put an emphasis on bonds that are moving. So there is double bonds here at particular points, and then we're effectively moving that negative charge all around the ring. And I want to put my partial charges in. So oxygen ends up being partial positive, and then notice here we're going to have delta minus on the ortho and para carbons. And what that means is that the ortho and para carbons are better nucleophiles than the metacarbons are. So you're going to have a preference for groups to be attacked by these carbons versus the metacarbons. So once again here it's more reactive, and we say that it's an ortho-para director. Okay, we can show an additional explanation of this by go ahead and showing the difference between what if it went orthopara versus going meta. And you do see differences in the resonance structures here, intermediates. So what I want to go ahead and do is say start with phenol again, and we're just going to say some generic electrophile. Doesn't really matter which one, because it only matters what's already on there, not what's coming in. That has the effect. So let's go ahead and start with our phenol, and any of the electrophiles we talked about earlier can work here. And I'm going to go ahead and show this reacting in the para position. I do recommend that you try the ortho substitution instead, and you're going to see that the mechanism is pretty close, just the resonance structures happen in a different order. But you should get all the same resonance structures if you're doing it correctly. All right, so in order to have this be in the para position, I'm going to use this double bond down here, like so. Go ahead and attack. And then we get our rhenium ion. And we're going to have an E here and an H there. And then now this puts the positive charge on this carbon. We got our OH, like so. All right, and then as you expect, it's resonance structures time. So we go ahead and show this here. We're going to be chasing the positives again because we have a positive charge to move around the ring. And then at this resonance structure, we now have a different situation than we've seen before when we just had the one group on there. All right, so double bond, E and H. All right, so at this point, we have a positive charge right here, and then one atom away, we have a lone pair. So what can happen here now is we have an additional resonance structure that's pretty much like our carbonyl resonance. So this comes down, and we now have an additional resonance structure. You do not get this resonance structure if you have this go meta. And I'm going to go ahead and show that today as well. So double bond there, like so, and plus charge is now on the oxygen, E, and then H. All right, so I want to put an emphasis on that resonance structure. We do not get that resonance structure if this goes meta instead. That. Recall that more resonance structures means more stability, so this is going to be the preferred path. So we have two things happening here. One thing is originally we talked about the resonance of the starting compound making these carbons more reactive as a nucleophile, and then we also have the additional effect of we get extra resonance structures in the intermediate. All right, let's go ahead and finish this up. So what do we do here next? We're going to go ahead and push this double bond up here. And this is going to go back. New resonance structure. We're now in the situation where the plus charge is straight next to that carbon. I'm moving the H to this side now just for the ease of the drawing, but it doesn't really matter. All right. So here you go ahead and show whatever your base is. Remember, this is different depending on which specific reaction you're running, but either way, it's an E1-like elimination step. So boom, boom, get our benzene back, and we get a net substitution in the para position. All right. Okay, so let's go ahead and show the same reaction again. In this case, I'm going to go ahead and show it going into the meta position, where it's not supposed to go. I want to do the wrong answer now and see why it's wrong. So here, here, here. And just like the last one, we're going to go ahead and use a generic electrophile. So we want this carbon to have the group, so I'm going to use this double bond to do it. So boom. It really should go to the para position, but I'm going to go ahead and show it the wrong way by having it go here. That now puts the plus charge in the para carbon. And then we have our double bonds, which can then do their magic. All right, so this goes towards the positive. We get a resonance structure. Plus charge is now here. And then double bond there, double bond here. And then we had our groups over here. All right, it works out we only get one more resonance structure here, where the last one we had 4 resonance structures. This time we're only going to have 3. And the reason why is because you notice how the resonance here works. That plus charge is going to skip that carbon when we have this go into the meta position. So where your plus charges end up at is different depending on how you have the groups go on there. And you'll start recognizing this if you get enough practice with your resonance structures. Oops, almost made a mistake. So it's going to be over here. All right, and then you go ahead and show whatever base you're working with. Go ahead and give you the elimination step, giving our benzene back, and then we have the wrong answer of having a donating group directing meta. Remember, that's incorrect. We do not like to show this for the reasons I just explained. So if you did that, I would do this as a response. That's the wrong answer. So orthopara directing. So just to recap here, two explanations for this. The first explanation is starting with the original compound before any reaction happened. We look at the resonance of it, and we see that the negative charges end up on ortho and para carbons, making those carbons more reactive than the meta ones. The ring is also more reactive than the nucleophile as a whole. And then if you have the reaction go ortho or para, you will end up with an extra resonance structure here where you have a double bond kind of going towards the oxygen. I do want to mention here, though, that if we were using an alkyl group, which is technically a orthopara director, you get a more stable intermediate. With this one right here, that would be tertiary if that were a carbon group. But it's not in this case. In the case we have lone pairs, we can get an extra resonance structure. So either way, these groups are still directing the same way. And then if you show it go meta, the wrong route, you get less resonance structures, meaning this is not the preferred path. All right, let's go ahead and take a look at what happens when you have a withdrawing group on there. You're going to see we have a lot of the reverse situations that we had with the donating groups. So remember that these withdrawing groups make them less reactive. And for this example, I want to use the strongest withdrawing group that we're going to talk about in this class, the nitro group. This is the strongest withdrawing group. So when showing the resonance for nitro groups, you want to actually draw out the structure of the nitro. And you have a double bond, single bond situation here, and plus charge on nitrogen. Notice here with the general trend for the withdrawing groups, either you have a full positive or a partial positive on the atom directly attached to the ring. And so what ends up happening here is instead of pushing electrons towards the ring, we're now pulling away from the ring. So I'm going to go ahead and show that. So this double bond moves up. This pops out that way. So then we get our intermediate, resonance structure here. So plus is now there. And nitrogen still is positive, but we now have a second negative over on the other oxygen, like so. And then the other groups didn't do anything yet. All right, and in this case, we're going to be chasing positives again, so go ahead and move this over here. And if you're thinking about what happened with the last mechanism, notice here I'm going to end up with positive charges now on the ortho-paracarbons, making them less reactive. So double bond now here, double bond NO plus minus minus. And then that plus charge here. All right, and then you go ahead and chase the positive some more, so like so. So now we have the plus charge at the paracarbon, and this resonance structure is going to end up in the ortho carbon, like so. And I'm just going to shorthand this for NO2 for now. All right, last resonance structure. Oops, I can't do that. We got to actually show those arrows. That's what I get for being lazy. All right, so negative, negative, positive. All right, so we're going to show the reformation of the nitro group. And just for fun, I'm going to show that there is resonance in the nitro group that does that. So the other particular NO bond could be double on the other side. All right, we get our benzene back now. So double, double, double. And now I can shorthand the NO2. We're not doing anything else with it. All right, so taking a look at the overall resonance hybrid for this, we have the exact opposite situation that we had with the donating groups. So this time you're going to end up with delta positives on ortho and paracarbons. So delta positive, delta positive, delta positive. So what ends up happening here is EWGs make this benzene less reactive. And then just looking at resonance here, we're going to see that the metacarbons are more reactive now than the ortho and paracarbons are. So here we go ahead and have this meta directing. Okay. In the situation where we take a look at the reaction, if we have it go the wrong route, I think the only thing you really need to take a look at here is if we have it go wrong, because you end up with a situation where you have a very high energy intermediate. If you have this go meta, you're going to end up with the same situation where you have the three typical resonance structures. The main thing I want to point out here is if you have this go ortho or para. All right, so let's go ahead and start with that. So nitrobenzene, once again, does not like to undergo EAS reactions very readily, but we're going to go ahead and show it do that anyway. E+, and I want to have this go the wrong route and have it go orthopara. So I'm going to use this right here. So then we get the arenium ion intermediate to H, and whatever our electrophile is, plus charge is now there. All right, and then we have our NO2 group still attached. So chase the positive, move this down this way. And then here we have the problem, why this does not want to go orthopara. And I want to go ahead and draw out the nitro group. All right, plus charge, and notice now where the plus charge is going to end up, it's directly attached like that. So hoping you're seeing a problem with this resonance structure. It's this portion right here. So here we see that there are two adjacent like charges. Nature does not like that. So it's going to prevent this by having this just go the meta route. If you have this go the ortho route, you're going to have the same situation where you have this high energy resonance structure. So not good. Does not go this way. So we say we have a high energy resonance structure. You do not get this if you have this go meta. You'll end up with the plus charges avoiding that particular carbon. All right. All right, let's go ahead and take a look at some actual problems here. So a typical synthesis problem in this chapter is where, starting from benzene is going to be our common starting point, and you have to put groups on it. And the main trick here on putting these groups on correctly is the order that you put them in. Just like cooking, the order that you put things in the pot matters, right? So I want to go ahead and start with a pretty straightforward example. This, like that. So what you want to do is you want to take a look at both groups that are attached on there, and you want to think about whether they are withdrawing or donating, and what kind of director they are. So we have two choices here. So remember that bromine is a withdrawing group, but it's an orthopair director. So if we were to put this group on there first, it would direct the second group here. And the problem with that, though, is that remember that bromine is also a withdrawing group, so it makes it less reactive. So you're going to get a pretty low yield with this here. An alternative way would to be to go ahead and put the alkylation first and then brominate. That's probably a better route because we're going to get more product at the end. So to do this, all we do is start from benzene. I'm going to put the circle. I don't like drawing them this way, but just for short, we're not doing any resonance here, so it's fine. All right, so I want to go ahead and do the alkylation first. So this is the Friedel-Crafts alkylation with AlCl3. You go ahead and put the ethyl group here. We don't have to worry about rearrangements here because there wouldn't be any. And then we get our ethyl benzene. And then next we go ahead and throw in Br2, FeBr3. I am going to be particular about this. You do need the catalyst here. It's not just bromine. We do need the iron catalyst. And then we go ahead and put that there. And then the bromine here is in the para position. All right, a more challenging problem would be if these were meta-substituted. So instead, we're going to start with benzene again. And then now we want to get this a similar product, but instead of having it be para, we want to go ahead and have this be meta instead. We have to take a different approach here. So the problem with this situation here is that they're both orthopara directors. So what do? I did show you guys there is a way to put a withdrawing group on there first with the alkyl group as an acyl group. And that's going to be the route we use instead. Because acyl groups are meta-directors, so this will work. All right, so starting with benzene, we're going to go ahead and use the corresponding acid halide. We need 2 carbons. So chlorine with 2 carbons, don't forget we have that. And then we have AlCl3. And then we go ahead and get acetophenone now. I'm drawing the double bonds here. All right, we get that. And then now we could reduce it, or we can't reduce it now because we need to make sure we keep this as a meta director before we do the reduction. So here we need Br2, FeBr3. And then you go ahead and put the bromine now in the meta position. And once again, here is because of the acyl group being a meta director, so this does work. All right, and then the last step here, you want to go ahead and do the Clemmensen reduction. So you don't want to do a borohydride or lithium aluminum hydride reduction here because you're going to get an alcohol that you have to get rid of then. So we can do it all in one step. So this is zinc, mercury, hydrochloric acid, and heat. Remember, this is called the Clemmensen reduction. We got all these named reactions now. Clemmensen reduction, and that gives us the target. Okay. Another situation you may have to deal with is getting the ortho product, which is actually pretty problematic sometimes because these orthopara directors have a tendency to push the group into the para position due to steric hindrance. So I want to go ahead and do the same problem again, but this time I want to go ahead and see if we have an ortho product instead, and how do we do that? All right, starting with benzene, what I'm saying here is we want to get to the ortho product. So Br here, and then ethyl over here. And what do? Okay, so I would go ahead and start off this problem with the alkylation. We don't need to do acylation here because we're just putting an ethyl group on there that would not rearrange, so we don't have to worry about it too much here. Remember though, in the lab, there is a real life restriction here in that this ethyl benzene is more reactive. You're probably going to get multiple alkylations, but it's fine on paper. I'm not going to be that picky with you guys. All right, the next thing I want to do here is I want to put a group on here, but I want to block this carbon. And the reason why is because if I block this carbon, I can then direct the next group to go to the position I want the bromine at. The way we do this protecting here is fuming H2SO4. This was the sulfonation reaction, and it puts a sulfonic acid on the benzene. But notice how it's going to work here. This is an orthopara director. It's going to direct the group to go here. So here we have our SO3H attached. Now you go ahead and do the Br2 FeBr3. All right, so let's take a look at what's going to happen here. We have two things pushing the bromine to this position. The two things doing this here is that one thing here is we have a activating group here that's directing orthopara. Para is blocked, so it can only go ortho. Additionally, the group that on this side here is a meta director, and this is also doubly directing this here. I do want to point out here that if you have multiple groups on there, the stronger activator dictates the position. So the main thing I would be looking at here is a stronger activator, which is the ethyl group. We'll go over that more in a few minutes. All right, to bring it back, we just throw in some water. It gets rid of that group, and we now have a net substitution in the ortho isomer. So if you want to do the ortho product, you're going to have to protect the para carbon. Otherwise, you're going to get para product major. The ortho product is minor, and we get none of the meta product. Okay. Did mention a moment ago that if you have multiple groups on there already, and so suppose you had like two groups on there and you want to add a third one, it works out where the stronger activator dictates the next position. So typically the ones that have the lone pairs are the stronger activators. So here I want to go ahead and use a methyl group as on here already. Notice here, so the problem here is that suppose I wanted to do the reaction, I want to add a chlorine on there, like so. Now where does that chlorine go? Notice here that the para position is blocked relative to each other because it's para substituted already. And then if the group goes here, it's ortho to the amine, but it's meta to the methyl group. So remember that the stronger activator dictates, so it's going to prefer to go here. If it were to go here, it would be meta to the stronger activator, which is the incorrect position. So I'd make the argument that it would go there, because the stronger activator is the amine, the stronger activator dictates the position. If you have a situation where one is withdrawing, one is activating, that's pretty straightforward. The activator dictates, not the deactivating group. All right, we get our CH3 group. Another issue that you may come across is that if you have an amine on there and you have your reaction in acidic conditions, you change the directing effects on the amine group. We saw earlier that if you have a protonated amine, it's meta-directing. So we'll see how what kind of problem that causes and how we avoid it. All right, so suppose we're starting here with aniline, NH2 on the benzene ring, and then I wanted to run a nitration reaction. So this was HNO3, H2SO4. You may notice here that this particular amine can act as a base. And recall that acid-base reactions happen sooner than anything that's nucleophile electrophile. They're very, very readily happening. So what ends up happening here is we get a protonated amine reacting with either one of the acids here, NH3+, and then this group is going to direct meta. So what ends up happening here is we're going to get the meta product instead, and not the ortho product that we want, or orthopara product that you might have wanted. All right, so there is a way to get around this. We have to use the reaction that we're going to be covering in more detail in the next section, but for now I want you guys to just know the reaction. We'll do the mechanism later. So what we have to do here is acylate it. So starting with aniline, we have NH2, and then here we can use an acid halide, or you can also use an anhydride. And notice here, I'm not going to put the catalyst here. If you don't put the catalyst here, it's, the nucleophile is going to be the amine, not the benzene, because we needed the catalyst here to make this a better electrophile. But in this case, if we don't have the catalyst, what's instead going to happen is the amine is going to react. So we effectively protect this amine. So NH, and then we now have an amide instead. So we went from an amine to an amide. And I also want to mention here that amide, the lone pair on the amide nitrogen is not basic. Can you guys think of why? I talked about it last time. Let's see if you guys can remember or not. It has to do with resonance, of course, right? So, this is how we do this. And then we did not change the directing effects of this particular compound because we still have a lone pair there. It's still going to direct orthopara. It's just now protected. So now we can go ahead and run our chlorination reaction with Cl2, FeCl3. And get your benzene. We got our amide group on there. And then chlorine. Right, and then you can go ahead and just do, oops, that wasn't the right reaction. But you guys get the point. Yeah, it should have been the nitro. But anyway, if we try to get the chlorine here, you just do H3O plus and heat. What ends up happening here is it does an acyl substitution, and we're gonna pull this off as a carboxylic acid group, and then we're gonna get our amine back. Once again, do not worry about the mechanism for the acyl substitution part. We're gonna cover that in detail during all the carbonyl stuff we're doing in a few weeks. And boom. All right. So all right. All right, guys, I got one last reaction to show you guys for today, and this is oxidation of the benzylic position. So oxidation of benzylic carbons. All right, so this is pretty straightforward. All we do is we have our benzene, and we have a carbon here, a benzylic carbon, and you must have at least one H there. If there's no H on this carbon, this does not work. So, and it also does not matter what the R groups are. They can be, 2 carbons long or 300 carbons long. Does not matter. So the conditions here are KMNO4, potassium permanganate, and heat. And what you get is benzoic acid. It oxidizes that carbon to a carboxylic acid. All right, so there are better ways to get carboxylic acids, but before I go over that here, I did want to show you a situation we have here. So suppose here we had, say, a methyl group on there, and then let's say over here we had a tert butyl group. If you were to run the oxidation with this, you do not oxidize both carbons here because we cannot oxidize this carbon here. If you were to show a double bond O there, you would violate the octet rule. Additionally, we're not going to go over the mechanism, but the way the mechanism works is you need that H there. That's basically like a point where the oxides can chew on the molecule. So what happens here is we get the methyl group becomes a carboxylic acid, and this group is unreacted. All right. A better way, I think, to make a benzoic acid is to instead make a Grignard, and there is a Grignard reaction I want to show you here that kind of goes in this section. So suppose you're starting with benzene, because that's going to be the common starting point, and you want to turn it to a Grignard first. The way we do that is Br2 and FeBr3 to brominate. So you go ahead and put the bromine there, and then we do our standard magnesium and ether to get the Grignard, like that. So then we get MgBr on here, and that is a excellent nucleophile now. And then the reagent here that we use is carbon dioxide. So CO2, it turns out that CO2 is electrophilic and can be reacted with nucleophiles. You may recall the reaction with CO2 and water. turning into carbonic acid. That's actually a nucleophile electrophile thing, but we'll see that later. All right, so boom, attacks this. We get the carboxylate from this. The carboxylate is basically your carboxylic acid before it's protonated. So we have an O- on there. And then to get to the OH, all you have to do is the quench step. Pretty straightforward. We always have the quench step in working with these organometallic compounds. And this is now a better way to get to your benzoic acid. In general, these permanganate reactions are not done in lab all that much, except for staining things like TLC plates. It's typically what we use them for. We typically don't use them for synthesis reactions. All right, so now it's just a matter of practice. We are now officially done with the benzene chemistry for now. We are going to go over SNAR reactions, but I'm going to say that for after the test. So if you run across the SNAR mechanism and benzyne chemistry, this right here, if you run across this kind of stuff, we are doing this after the test, probably the Tuesday after the test. All right, that's pretty much it for today's lecture. I'm hoping you're going to enjoy your snow day in Las Vegas and have a good weekend. I'll see you guys next week.